One major operation for process management is process scheduling. The goals may be various for different systems. For a batch system, the main goal is to maximize the CPU utilization, to keep the CPU as busy as possible. So which means to minimize the idle time of a CPU. Because in most of the batch system, CPU is the most precious resources. So that is why we want to fully utilize it. On the other hand, in time sharing system, the main goal may become to quickly switch processes onto the CPU to make the response time as short as possible for each user. From the perspective of users, so they will feel that so they are the only user who use the computer system, which means the user does not realize that so more processes actually are running on the background of this operating system. To do the scheduling, the operating system needs to maintain a lot of information. More specifically, the operating system need to maintain numbers of scheduling queues of processes. For example, the job queue will hold all the processes submit to the computer system. On the ready queue, all the processes in this queue are under the ready state. So which means that whenever the CPU is available, the chosen processes in the ready queue can be put on the CPU and get executed immediately. So in the computer system, usually has a multiple device queues. So each device will maintain a device queue. For example, numbers of processes, they need to do some I/O on a same device. Then those processes will be put on the device queue of that device and waiting for the I/O there. Surely their state will be switched to waiting as well. So during the lifetime of a process, it may not only change the state from time to time, but also migrate among various queues. For example, at the very beginning, a process has been added into the job queue. So when the process gets admitted, the process is put on the ready queue. So when the CPU is available, the process can be put on the CPU and executed. So when the process need to do some I/O, it will also be put on the device queue. And also the operating system will run an algorithm called process scheduler, which will make a decision to decide which process can be put onto the CPU next. And this process must be chosen from the ready queue. As we already mentioned, only the processes on the ready queue can be put onto the CPU immediately. This slide shows us an example of queues that we just talked about in the previous slide. So for this ready queue, it is maintained by a linked list. So multiple PCBs for different processes are in the ready queue and ready to be executed on the CPU. And also here we have different device queues. For example, this magnetic tapes, so we do not have any PCB on their queue. However, on this hard disk device queue, so we have 3 PCBs. And each one is waiting for the I/O there. So surely they are under the waiting state currently. At the last example, so we have a PCB on the terminal device queue there. So maybe it is waiting for the keyboard input from the user or waiting for some output to the screen. Remember, the algorithm that can decide on which process can be put onto the CPU is called a scheduler. So in general, there are different types of a scheduler depends on the time scale. So the first type is called the short-term scheduler. So we often call it CPU scheduler. The CPU scheduler will decide which process can be put onto the CPU to be executed. And sometimes it is the only scheduler in the computer system. So you can imagine that it can be invoked very quickly or very frequently. So most of the time in millisecond level. That is why we call it short-term scheduler. So since it will be invoked very frequently, it must be running very fast. Because within 1 second, the CPU scheduler can be invoked 10 times or even hundreds of times. If the CPU scheduler is running very slow, so the performance of a computer system will be slowed down as well. So for example, suppose when the CPU scheduler gets invoked, so it will take 1 second, and then run the process for a couple of milliseconds, then the CPU scheduler will be invoked again, right? And another 1 second will be taken to run the scheduler. Then you can imagine how slow the system can be. And also it is unacceptable. Therefore, the CPU scheduler must be run super fast. On the other hand, so we have another type of scheduler, which is called a long-term scheduler. So we also call it job scheduler. So if you still remember, we have a talk about the job queue, all the submitted processes which are not admitted to be executed, so they will be put on the job queue first. And then the job queue will decide which job can be put onto the ready queue and later get executed on the CPU. So this scheduler is often invoked infrequently. So it is in second or even minute level. So this scheduler can be running slower, and also the job scheduler can be designed very complicated. So the main goal of a long-term scheduler is to control the degree of multi-programming. So this term may be fancy to you guys, but actually it is quite simple. The degree of multi-programming means that a number of processes are currently running on the computer system. So when define the algorithm for a long-term scheduler, if we only allow one process that can be moved from a job queue to ready queue, the degree of multi-programming is pretty small. Otherwise, the degree of multi-programming can be very large. Another major goal of a long-term scheduler is striving for good process mix. So in general, actually there are two types of processes. One is called the I/O bound process. The major operation during the entire process life is to do the I/O. For example, the process is reading a file or writing something into a file. And the other one is a CPU bound process. So you may already know that the major operation of this type of a process is CPU demanded. So you can imagine the two extreme case. One is that all the processes loaded into the CPU or loaded into the computer system are I/O bound process, and the I/O device will keep him busy. However, the CPU will be idle there for most of the time, right? The other case is that all the processes are CPU bound process. So the CPU is keep beating there, and the I/O device are idle. In order to improve the performance of a computer system, to keep both CPU and I/O devices busy, so we need to achieve the good process mix. So which means both loading the CPU bound processes and the I/O bound processes at one time. Remember, I have illustrated how the CPU can switch processes in the previous slides. So there are two major operations. One is that, so before the old process need to take off the CPU, the operating system will save the state of the old process in its PCB. The other operation is that, so before to put the next process into the CPU, the operating system will restore saved state for the next process. So there is a special term for these two major actions, which is called context switch. So now you know that the context switch only happened when CPU switch from one process to the others. However, for this procedure, it can benefit nothing to the user's process. So that is why we treat it as an overhead. the performance of context switch depends on numbers of factors. So one factor is the complexity of operating system and the PCB. So this factor is very easy to understand. The larger the PCB, the longer context switch will be, right? So remember, we have talked about how to implement the PCB in Linux operating system. So if we add more member variables into the PCB structure, the size of the structure will become larger too, right? Then the time to load the PCB will be longer as well. So that is why more complex the operating system and the PCB can cause a longer context switch. So nowadays, we may have a hardware supported to reduce the overhead of a context switch. So for example, traditionally, we only have one set of registers inside the CPU to remember the state of process. So especially for the single CPU with a single core. So when the operating system does the context switch, so all the state of the older process must be moved out of the registers and put them into its PCB. However, so actually we can add multiple sets of registers into a single CPU. So for example, we have 3 sets of registers inside this CPU, just like we have illustrated on the bottom of this slide. So you can see here in this computer, we only got a single core CPU, but we have 3 sets of registers. So and we can have a dedicated register for the process 1, and have another register set for process 2, and the rest register set is for the process 3. So you can see that. So when process 1 loaded into the CPU, we can save the state of a process 1 in the first set of registers. So when the context switch happened, we can keep the state of a process 1 in first set of registers. So we just put all the state of a process 2 on the second set of registers. So then execute the process 2. So similarly, things for process 3. So when we need to run process 1, we can directly reconnect the first set of registers to the CPU core and execute it. However, this case only works for 3 processes. So if you have more processes needed to be executed, so you still need to move the state of all the processes back to their PCB. But the performance is already improved a lot compared to the single set of register hardware.